Before we go any further into chapter 3, we need to talk about this. Higher order derivatives. In the book, they're just going to throw this at us, like in homework questions and things. So we want to have a little bit of a leg up, talk about it before that happens. So let's take a look at f of x equals x to the fourth minus x to the third minus 8x squared plus 5x plus 1. We know that the derivative, there we go, would be 4x cubed minus 3x squared minus 16x plus 5. And the plus 1, that derivative would be 0. So there you are. Now you notice that the derivative of this polynomial is another polynomial. And you might say it's even a simpler polynomial, just the way the powers are working here. What's stopping us from taking a derivative of the derivative? Certainly we could. Now you might be asking, like, why would you do that? Like, the derivative is the slope of the tangent line on a graph. What does a second derivative mean? Don't worry about that right now. We'll get there. Let's just perform it. We could take another derivative here, which we would call f double prime of x. And that would be 12x squared minus 6x minus 16. Hey, why stop there? Let's do it again. F triple prime of x, 24x minus 6. Let's do it another time. Now, when we get to a fourth derivative, we're no longer going to use the primes. I think the reasoning is once you get to 4, that's a lot, and that's kind of difficult for the eye to discern how many primes there are once you get past 3. So instead, the notation people use is a set of parentheses with a 4 there for the fourth derivative. Why not just a 4? Why the parentheses? Because we wouldn't want that to be confused with like an exponent, like to the 4th power. So we put a little set of parentheses there, then everybody knows, okay, they're talking about the 4th derivative, and that would be 24 here. Hey, why not a 5th derivative? Well, now, because we just have a constant, the 5th derivative is 0, but that doesn't mean we can't do any more derivatives. We could do as many as we like. A 6th derivative, well, it'd still be 0, but we could keep going and going and going if we wanted to. Okay. So this was all using the f prime notation. Let's take a look at just what some other notations would show up as. So a first derivative, here's what we would see, right? F prime of x, y prime. We might use the Leibniz dy over dx, or this version of the Leibniz where we fill in the expression for the function. A second derivative, f double prime x, y double prime. Okay, what about for the Leibniz? Here's what it would look like. D squared y over dx squared. Now that's kind of strange. I'll explain why that is in a moment. And for this style, kind of similar, d squared over dx squared. And then, of course, we'd fill in whatever we were going to take the second derivative of. So that would actually be the original function would be inside, since this would say take the second derivative of what you see here. How about a third derivative? Similar, triple prime, triple prime. Now we use a 3, right? And a fourth derivative, and that's where we start using the parentheses, like we said. For the y, it would be a y. Fourth derivative of y would look like that. And then, of course, we have the 4s here and here. Okay, so why do we see this, d squared y over dx squared? We can explain that. Because, if we're thinking a second derivative, that's the derivative of a derivative. So think about saying, okay, let's take the derivative. It's almost like we're using this notation now, but with dy over dx inside, we're going to take the derivative of dy over dx. Now, this is kind of, cumbersome. We wouldn't want to have to write that whole thing. So instead, people write it like this. Now, here's the thing. This is not a fraction. This is not a fraction. This is not multiplication. either, but the notation kind of lends itself to that. So if this was a fraction and this was a fraction and this was multiplication, which it isn't, then the d's would multiply and the dx's would multiply, and we'd get d squared y over dx squared like that. So it's kind of a play. It's almost like a pun. It's kind of like a play on the notation. You know, pretend like it was a fraction and this is how it would work. And so we'll just use that. And it makes it a little bit nice and neat. And it's clear that we're talking about the second derivative or the third or the fourth that way. Okay, one other thing I need to say here. How would higher order derivatives, how would those apply? Just what kind of applications would that look like? So, you know, the first application that we see of derivatives is instantaneous velocity. So let's go with that. Let's imagine that the position of an object is s of t. S of t is the standard way to represent the position of an object. Why don't they use p of t? I'm not really sure. They use s of t. So like the position at time t. Okay. Well, the velocity of that object would be the derivative. You could think of it as s prime t, but usually we just represent it as v of t. And we all know that v of t is the derivative of s of t. Okay, so what would going further mean physically? If the derivative is the velocity, it's like the instantaneous rate of change of the position, then what would the next derivative be? The instantaneous rate of change of the velocity. Now, whenever I'm teaching this, you know, in a classroom, I usually put that out. And usually a few people know, if your velocity is changing, we call that acceleration. So think my velocity is increasing, right? That means I'm accelerating. I'm hitting the gas in my car and I'm going faster and faster. My velocity is getting higher and higher. I'm accelerating. I could also decelerate if I start slowing down, right? Okay, so that's s double prime of t. You know, I guess you could say that. I guess you could say v prime of t, but typically people just say a of t. And we all know that that's the second derivative. Now there is one more. We don't really see this a whole lot, but what if we went to a third derivative? What's the instantaneous rate of change of acceleration? This is not something we really think about, although we do experience it, say if we drive. What if your acceleration is changing? So let's say at first, right, you're accelerating, you think you've got an open road ahead of you, you're punching the gas, and then all of a sudden, maybe you see some cars ahead of you starting to slow down, or maybe there's a red light and you didn't anticipate that. So you slam on the brakes. Okay, so you were accelerating in a positive direction, and then you hit the brakes and you changed your acceleration and you started slowing down. What happens to you physically when you're driving in that car? Well, you know, the driver is one thing, but like any passengers, for sure, like you're accelerating, it's like you feel yourself getting pushed back into the seat, if it's very much, and then you hit the brakes, and what happens? You get thrown forward. We literally call the third derivative the jerk. As your acceleration is changing, it's literally jerking the individual experiencing that, right? So that's the third derivative of the position. The second derivative of velocity, it's the derivative of acceleration, or what we would just say, we just call it J of t for the jerk. All right, you guys, you're going to see questions, if something comes up and it's like, hey, find the acceleration at such and such, okay, they're talking about the second derivative. And then maybe you need to plug a number in or something to find the acceleration at a given moment, or velocity first derivative. All righty, let's stop this one here.